Welcome back to the deep dive. This is the place where we go beyond the surface, really get into the source material, and try to build some genuine, high-level insight. We're not about summaries here, we're trying to understand the why.
And today, the why is focused on just an incredible figure, one of the most recognizable and yet maybe one of the least truly understood people of our time, Stephen William Hawking.
Absolutely. He lived from 1942 to 2018, and he really had this singular, almost contradictory identity.
He did. On the one hand, you have the brilliant English theoretical physicist, the cosmologist, the mind trying to unify the entire universe. And then on the other, you have this massive cultural icon who battled motor neuron disease for more than 50 years and achieved, well, a level of fame no scientist had seen in generations.
Right. And that's our mission for this deep dive. We're going to unpack that narrative, the connection between the intense academic rigor on a cosmic scale and, well, the profound physical collapse of the man himself. We've got biographies, articles, scientific papers right here, and we're looking for what explains it.
How does someone get a terminal diagnosis at 21?
And then go on to hold the Lucasian Professorship of Mathematics, Isaac Newton's old chair.
Exactly. From 1979 all the way to 2009. It's a story that weaves together this really radical physics with an almost unimaginable personal struggle.
So for you listening, here's the plan. We're going to start at the beginning. His very unusual origins, that famous apathy he had as a student, and then the shock of the diagnosis that really lit a fire under him.
And we'll get straight into the physics, the really big ideas.
Yeah.
Singularity theorems, the famous black hole wars, and, of course, the breakthrough of Hawking radiation.
And finally, we'll look at the man himself. His shift to global celebrity, the fierce independence he kept through it all, and his pretty striking final views on AI, space, and really the future of all of us.
It's quite a journey.
Okay, let's start unpacking this. Where does a mind like Hawking's come from? And the sources point to a family that was, well, anything but conventional.
That's a good way to put it. His parents, Frank and Isabel, were both Oxford graduates. Frank was a respected medical researcher in tropical diseases, and Isabel studied philosophy, politics, and economics. So, a very academic household.
But not a wealthy one. That's a key detail.
Not at all. They were frugal. They lived in Highgate, London, then St. Albans, and the sources paint this picture of a highly intelligent and somewhat eccentric family life.
And that eccentricity, it seems crucial. It wasn't just being smart. It was a rejection of kind of normal social roles.
Oh, completely. The classic story that gets repeated is about their family meals. They weren't spent talking.
No, each person had a book. They would just sit there in silence, reading.
I mean, can you imagine? And their family car, this really sums it up, was a converted London taxi cab. They bought it cheap. It was big enough for the family and all their books. This was an environment that prized independent thought above almost everything else.
But maybe not discipline.
Definitely not conventional discipline. And you see that immediately in his school years. It's actually really surprising. The future Lucasian professor was not a star student.
He struggled to learn to read, didn't he?
He did. He blamed the progressive methods of his school at the time. Said he didn't learn until he was much older than his peers.
But his friends saw something else. His nickname was Einstein.
Exactly. Because his raw aptitude was obvious, even if his grades were mediocre. He and his friends, with a little help from a math teacher named Dikran Tata, actually built a computer.
Wait, a working computer? In the late 1950s?
A working electromechanical computer. They used old clock parts, a telephone switchboard, just recycled junk. And this wasn't for a class project or a grade.
It was pure curiosity.
It was a self-directed passion project. It showed he understood systems and logic in a way that, his report card just couldn't capture.
That's the classic sign of genius, isn't it? Not good at the rote learning, but brilliant at seeing the whole system. So when it came to university, he wanted math.
He did. But his father wanted him to study medicine. And to complicate things, University College at Oxford, his dad's old college, didn't offer a straight mathematics degree.
So he chose physics and chemistry instead.
A compromise. And he starts at Oxford in 1959. He's only 17. And he is, by all accounts, immediately bored and lonely.
He found the work ridiculously easy.
That's the famous quote. His physics tutor, Robert Berman, said Hawking just needed to know that a problem could be solved and then he could figure it out himself without looking at how anyone else did it.
That's incredible confidence. But it led to some terrible study habits.
Terrible. He himself estimated he only studied for about 1,000 hours in his entire 3-year degree. That's, what, an hour a day? maybe.
So he's bored, he's not being challenged, and he's looking for some kind of intensity.
And he finds it in the University College Boat Club. He joins as a cox.
The person who steers the boat and motivates the rowers.
Right. And he becomes known for it. He develops this daredevil image, steering these really risky, tight courses, sometimes damaging the boats.
Yeah.
It was his way of finding that intensity and, becoming a more popular social figure.
But then came finals, and those study habits almost cost him everything.
They did. He needed a first-class degree to get into Cambridge for his graduate work in cosmology. And he was right on the borderline between a first and a second.
So it all came down to the viva, the oral examination.
This is where that audacity just shines. He doesn't go in there apologizing for his lack of work. He's completely pragmatic. The examiners ask him what his future plans are.
And he basically gives them an ultimatum.
He does. He says, if you award me a first, I will go to Cambridge. If I receive a second, I shall stay in Oxford, so I expect you will give me a first.
I mean, the nerve. But it wasn't just arrogance, was it? It was a calculated risk.
A completely calculated gamble. And it worked. Berman, his tutor, later confirmed the examiners knew they were dealing with someone far cleverer than most of themselves. He got his first. He was off to Cambridge in 1962.
So he arrives at Cambridge, ready to take on the universe, but it doesn't start well.
No, it's a difficult start. First, he's disappointed he doesn't get the famous astronomer Fred Hoyle as his supervisor. Instead, he gets Dennis Sciama.
And he also realizes he's not prepared.
Right. He feels his math skills from Oxford just aren't up to the task for general relativity. He feels completely lost in his early work.
And then on top of all that professional uncertainty comes this life-shattering personal crisis.
In 1963, he's just 21 years old. He's diagnosed with an early-onset, slow-progressing form of motor neuron disease, ALS.
The prognosis was just brutal.
The doctors gave him 2 years to live.
I can't even begin to imagine what that does to you.
He fell into a deep depression. He felt there was no point continuing his studies, no point in anything. He had just listened to Wagner and shut himself away.
But the disease didn't move as fast as they predicted. And that's the turning point, isn't it? The shock becomes a catalyst.
It becomes the ultimate motivator. It wasn't that the physical limits focused his mind, although maybe that was part of it. It was the realization that time was finite. He needed a purpose, and he needed it now.
And his supervisor, Sciama, encouraged him, pushed him to keep working.
He did. And Hawking's own words on this are so powerful. He said, "Before I got motor neuron disease, I was bored with life. But the prospect of an early death made me realize life was really worth living."
All that boredom, the daredevil stuff on the river, he was looking for stakes. And MND gave him the ultimate stakes.
And that new focus produced incredible results, incredibly quickly. By 1966, he finishes his PhD thesis, Properties of Expanding Universes.
Which got him a research fellowship at Gonville and Caius College. And he shared the Adams Prize with Roger Penrose.
That one year, 1966, was his arrival. He became a major force in physics and was born directly out of staring down his own mortality and refusing to give in.
Okay, so that collaboration with Roger Penrose really defined the first huge chapter of his scientific career. They started with the ideas in Hawking's thesis and just blew them up to a cosmic scale.
Right. What Penrose had already shown was that if a massive star collapses, it leads inevitably to a singularity, a point of infinite density inside a black hole.
But that's for a star. The revolutionary step was applying it to the whole universe.
Exactly. In 1970, they published this joint proof. It said that if the universe obeys general relativity, and if it's expanding in the way we observe, then it must have begun as a singularity.
So they weren't just saying the Big Bang was a good theory. They were saying it was a mathematical necessity of the laws of gravity as we understood them.
Precisely. And that was a huge blow to the competing steady-state theory at the time. It provided the mathematical backbone for the Big Bang model.
So what was the big hurdle they cleared? People thought singularities might just be, I don't know, mathematical quirks, right?
They did. Critics argue that maybe if you factor in rotation or a more complex, messy start to the universe, you could avoid everything collapsing back to a single point. Hawking and Penrose proved that no, as long as gravity is always attractive, the singularity is inescapable. The past of our expanding universe had to have a beginning.
From there, he zooms in on black holes themselves, and he starts with the laws of how they behave.
Yes, in 1970, he comes up with the second law of black hole dynamics. It's an elegant idea. It says that the surface area of a black hole's event horizon, the point of no return, can never get smaller.
It can only get bigger or stay the same.
Right. And working with others, they expand this into 4 laws of black hole mechanics, which strangely mirrored the laws of thermodynamics.
Strangely, because black holes are supposed to be completely cold, right? Zero temperature, zero entropy, which is a measure of disorder.
Exactly. So at the time, the analogy was just a formal mathematical curiosity, but it laid the groundwork for what came next.
And that groundwork also supported something called the no-hair theorem.
The no-hair theorem is just, it's one of the wildest ideas. It says that after a black hole forms, almost all the information about what created it is lost forever.
So it doesn't matter if it was a star or a cloud of dust or a giant pile of encyclopedias.
Doesn't matter. The resulting black hole is identical. It can only be described by 3 things: its mass, its electrical charge, and its rotation, or spin.
All the other details, the hair gets shaved off.
And that right there raises the massive question that would occupy him for the rest of his life. If the information is gone, where did it go?
Okay, so up to this point, everything is based on classical general relativity. Black holes are perfect prisons, they only grow. But then Hawking decides to mix in quantum mechanics and everything changes.
This is where it gets really fascinating. And it all started because he was trying to prove someone else wrong.
Right. He'd been talking to some Soviet physicists in Moscow in 1973.
Yakov Ildovich and Alexei Starobinsky. They suggested that rotating black holes should actually emit particles because of quantum effects. And Hawking was, by his own admission, annoyed by this.
Because it would violate his own second law that the area can never shrink.
Exactly. So he sets out to disprove it. And in the process of trying to prove them wrong, he proves them right, but in an even more profound way.
So what did he find?
He found a different mechanism that meant all black holes, not just rotating ones, must emit radiation. It's because of quantum fluctuations at the edge of the event horizon.
Okay, break this down for us. This is a tough one to get your head around.
So in quantum theory, empty space isn't really empty. It's fizzing with what are called virtual particles, particle and antiparticle pairs that pop into existence for a fraction of a second and then annihilate each other.
Okay, with you so far.
Now imagine this happens right at the edge of a black hole's event horizon. Sometimes one particle will fall in and the other will escape.
And the one that escapes is what we see.
Yes, a distant observer sees that escaping particle as real radiation. We call it Hawking radiation. But to conserve energy, if the escaping particle has positive energy, the particle that fell in must have had negative energy.
Which means the black hole's total mass and energy just went down.
Precisely. Black holes are not eternal. They leak. They lose mass, they shrink, and over an almost unimaginable time scale, they will eventually evaporate completely.
Which is a direct contradiction of his earlier work.
It is, but it also brilliantly solved the puzzle of the thermodynamics analogy. It proved that black holes do have a temperature and they do have entropy. This was a monumental breakthrough. The impact was immediate, and he was elected a Fellow of the Royal Society in 1974, right after the announcement.
And of course, we have to mention his first famous public wager, the one with Kip Thorne over Cygnus X1.
Ah, yes. This was less about a deep principle and more about, a real object in the sky. Hawking bet that this X-ray source, Cygnus X1, was not a black hole.
Which seems weird. Why bet against his own field?
He called it an insurance policy. He joked that he'd done so much work on black holes, if it turned out they didn't exist, he would have felt pretty silly. This way, at least he'd win the bet.
And he lost, right. He conceded in 1990.
He did. The evidence became overwhelming. But it was that playful public engagement with the science that really started to build his public persona.
So after revolutionizing black holes, he turns his attention back to the biggest question of all, the very beginning. In 1981, he goes to a conference at the Vatican, of all places.
And drops a bombshell. He proposes that the universe might not have a boundary, no beginning, and no ending.
This was the seed of the Hartle-Hawking state, which he published with Jim Hartle in 1983.
Right. And to get there, they used a very complex mathematical tool called imaginary time.
Okay, what does that mean in simple terms?
Well, it's a way of treating the time dimension as if it were another dimension of space. And when you do that, the Big Bang singularity, that point of infinite density where the laws of physics break, it just disappears. It smooths out.
This is where he uses that great analogy about the North Pole.
It's the perfect way to explain it. You can't go any further north than the North Pole, but the pole itself isn't an edge or a boundary on the Earth's surface. It's just another point.
So in this model, the Big Bang is like the North Pole, a starting point, but not a boundary where something had to, exist before it to create it.
Exactly. It suggests a universe that is completely self-contained. It doesn't need an external creator or a cause. As Hawking himself said, it meant God would not have had any freedom to choose how the universe began.
That is a profoundly philosophical statement coming from a physicist.
It was. It was a radical idea, suggesting the universe's origin was governed purely by the laws of physics itself.
And he kept refining this idea later in his life, right, with the top-down cosmology theory.
He did, with Thomas Hertog. This was a later attempt to deal with some tricky problems, like why our universe seems so perfectly fine-tuned for life.
Instead of a single starting point, this theory suggests there were many possible starts.
A whole superposition of possible histories. And the idea is that our present observation of the universe, the fact that we are here to see it, effectively selects the past history that is consistent with our existence.
So the present determines the past.
In a quantum mechanical sense, yes. It's a very complex idea, but it was his way of trying to create a complete and self-contained picture of cosmology.
So the science is established, the genius is recognized within the physics community, but the 1980s is when the rest of the world really discovers Stephen Hawking.
And the reason for it was surprisingly practical. It came down to money.
He needed to fund his children's education and his growing medical expenses.
Right. So in 1982, he decides to write a popular science book, something for the general public.
And the result was A Brief History of Time, published in 1988, and it just became this absolute cultural phenomenon.
The success was unbelievable. It was on the Sunday Times bestseller list for 237 weeks. That's over 4.5 years. It sold something like 9 million copies.
A book about cosmology with almost no equations in it.
That was the key.
Yeah.
And a lot of credit for that goes to his editor, Peter Gazzardi. He was the one who kept pushing Hawking to simplify, to make it more accessible.
The famous line was that every equation would have the readership.
Exactly. And Hawking, though he got frustrated with the constant revisions, he stuck with it. And it worked.
He became an instant celebrity. Newsweek called him the master of the universe.
He did.
Yeah.
But that level of fame brought its own problems. It created some friction within the academic world. Some of his colleagues felt that the media attention was more about his disability than his science.
That the visual of the man in the wheelchair was what made him a star, which, kind of overshadowed the actual work.
It's a complex issue. But that fame meant that his scientific debates, which usually happened behind closed doors in journals, were now playing out in public.
And nothing was more public than the black hole war.
Oh, this was the big one. This
Yeah.
was the intellectual fight of his career. It all comes back to Hawking radiation.
Right. If a black hole evaporates, what happens to the information about all the stuff that fell into it?
Hawking's initial position, back in 1981, was that the information is completely and irretrievably lost. It just vanishes from the universe.
And that's a huge problem for quantum mechanics.
A universe-breaking problem. A core principle of quantum mechanics is that information is never truly destroyed. It can be scrambled, transformed, but it's always there. If Hawking was right, one of the fundamental pillars of physics was wrong.
So you have general relativity clashing directly with quantum mechanics, and this led to a famous bet in 1997.
Yes, Hawking and Kip Thorne bet against John Preskill. They bet that information was lost. Preskill bet that it was somehow preserved and that our understanding of black holes had to be wrong.
And Hawking eventually conceded.
He did in 2004. But his solution was, well, it was very subtle. He proposed that if you consider all the alternative histories of the universe, information loss in one is canceled out by others. It wasn't a simple answer.
He even called his original idea his biggest blunder in 2014.
It clearly bothered him for decades. I mean, it's really telling us that his very last research paper, published after he died, was still trying to solve this problem. It was called Black Hole Entropy and Soft Hair. He was working on it right up to the end.
He also had another very public bet that he lost, this one about the Higgs boson.
Yes, he was very emphatic that the Higgs boson, the particle that gives other particles mass, would never be found. He had public debates with Peter Higgs himself.
So why was he so sure?
I think he felt it wasn't an elegant solution within the standard model. He hoped for something simpler, more fundamental. But, the universe doesn't have to be elegant.
And when CERN found the particle in 2012, the evidence was undeniable.
It was. And to his credit, he conceded immediately and gracefully. He publicly said Peter Higgs should win the Nobel Prize for it, which he did the next year. It showed he loved the intellectual fight, but he always respected the evidence.
So if we really want to understand his popular appeal, we have to look at this profound contrast. The mind that was expanding to fill the universe and the body that was collapsing. Let's talk about the reality of living with MND.
The decline started in his last year at Oxford. Just some clumsiness, a few falls. After the diagnosis in '63, it was slow, but just relentless. By the late 60s, he was on crutches, and by the mid-70s, he was in a wheelchair.
And he didn't just use the wheelchair, did he? He was famous for his driving.
Oh, notorious. The sources say he had a wildness to his driving. He'd zip around Cambridge, sometimes running over students' toes. It was a way of showing he was still in control, still independent.
That fierce independence seems to be the core of it all. He didn't want to be seen as a patient or a victim.
No, he wanted to be seen as scientist first and a normal human being. That mental strength was what allowed him to keep working. As he lost the ability to write, he had to invent new ways to think.
He started to see equations as geometry.
Exactly. He developed these incredibly powerful visual methods, manipulating entire complex proofs in his head. The physicist Werner Israel compared it to Mozart, composing a whole symphony in his mind without ever writing a note.
So the disability, in a way, might have actually changed how he did physics, making it more abstract.
It's possible. But the biggest change for his public identity came in 1985, when he lost his natural voice.
From a bout of pneumonia, right? He needed a tracheotomy to save his life.
It saved him, but it meant he could no longer speak. This was a critical moment. He needed round-the-clock care and a whole new way to communicate.
And that's where the famous computer voice comes in, the equalizer program.
Gifted to him in 1986 by a computer expert named Walter Woltos. At first, he used a handheld clicker to select words or letters from a screen.
And that voice synthesizer had that distinct American accent.
It did. A computer engineer named David Mason integrated the whole system onto his wheelchair. And as technology got better, people offered him newer, more natural-sounding voices, but he always refused.
Why?
He said he identified with it. He felt it was his voice. He even said he could communicate better now than before I lost my voice, because it forced him to be so clear and deliberate.
But the disease kept progressing. Eventually, he couldn't even use his hands for the clicker.
No. By 2005, he was down to controlling the entire system with just a single cheek muscle, detected by an infrared sensor on his glasses. His communication rate slowed to maybe 1 word per minute.
That's terrifying, the prospect of being locked in.
It was a real fear. So he started collaborating with Intel and a startup called SwiftKey on new software.
An adaptive system.
Right. They fed all of his books, lectures, and emails into the system so it could predict his next word with incredible accuracy. This custom-built software was absolutely essential for him to continue working and writing in his final years.
Through all of this, his personal life was obviously incredibly complicated. His engagement to Jane Wilde right after the diagnosis, he said it gave him something to live for.
They married in 1965, had 3 children, and Jane's role in those early decades was just immense. The sources really stressed the strain it put on their marriage, the constant nursing care, the demands of his health, on top of raising a family.
And there was a fundamental difference in their worldview.
A huge one. Jane had a very strong Christian faith, and Stephen, as his work progressed, became a more and more convinced atheist. That created a lot of tension.
And the marriage eventually ended. He left Jane in 1990 and later married one of his nurses, Elaine Mason, in 1995.
That second marriage lasted until 2006. But it was troubled. There were reports in the early 2000s from family and staff about alleged physical abuse.
And there were police investigations.
Yes, but they were always closed because Hawking himself refused to make any complaint or cooperate.
After he divorced Elaine in 2006, he seemed to grow closer again to Jane and his children.
There was a reconciliation, yes, and that provided him with a lot of support in his final years. It's that part of his life, that relationship with Jane, that was famously turned into the film The Theory of Everything.
He also embraced his role as a public advocate, didn't he? Even if he was reluctant at first?
He was, but he eventually accepted he was a role model, especially for disability rights. He campaigned for better accessibility in Cambridge, which, with its ancient buildings, was a real challenge.
And he had this one huge, unfulfilled dream: to go to space.
He really wanted to. Richard Branson offered him a flight on Virgin Galactic, and to prepare, in 2007, he took a zero-gravity flight, the Vomit Comet.
And the pictures of him on that flight, floating, free from his chair?
They're iconic. They became this incredible symbol of him for a moment, transcending his physical limitations. He passed all the tests, but sadly, commercial flights didn't begin in his lifetime.
He also wasn't afraid to be political. He used his platform.
He was a lifelong supporter of the UK's Labour Party. He was very outspoken. He called the Iraq War a war crime. He campaigned against nuclear weapons. And he was a massive champion for universal health care.
He credited the NHS, the UK's health service, with his survival.
He said flatly that without them, he would have died decades earlier. And he issued these very stark warnings later in life about Brexit, about Donald Trump's climate policies.
Yeah.
He feared we were on a path to turning Earth into a Venus-like planet, hot and uninhabitable.
In those later years, he really did turn his mind to these biggest of big questions: philosophy, God, humanity's future.
And he wasn't shy about his opinions. In 2011, he famously declared that philosophy is dead.
That's a bold statement. What was his reasoning?
He basically argued that philosophers hadn't kept up with modern science. He felt that the big questions that used to belong to philosophy, what is the nature of existence, where did the universe come from, were now being answered by physicists. He saw scientists as the bearers of the torch of discovery now.
And his own views on a creator, on God, they evolved quite a bit.
They really did. In A Brief History of Time, he uses that famous metaphor about wanting to know the mind of God. A lot of people interpreted that in a religious sense.
But later on, he left no room for doubt.
None at all. In his last decade, he was explicitly and proudly an atheist. He said, "I'm an atheist." His view was that the universe is governed by the laws of physics, period. The Hartle-Hawking models supported that. A universe with no boundary needs no creator.
He even described the brain as a computer.
Right. A computer that will stop working when its parts fail.
Yeah.
And he called the afterlife a fairy story for people afraid of the dark. His final view was that no one created the universe and no one directs our fate.
And that worldview, based on physics and probability, led him to some pretty stark conclusions about our survival.
He thought a global catastrophe in the next 1,000 years was almost inevitable. A nuclear war, a genetically engineered virus, an asteroid.
Something.
Which is why he was such a proponent of space colonization.
It was an imperative for him. Don't keep all of humanity's eggs in one basket. We have to become a multi-planet species to guarantee our long-term survival.
And if we do meet anyone else out there, he had a strong warning.
A very strong warning. Avoid contact. He feared that an advanced alien civilization would likely be nomadic, looking for resources. He compared it to Columbus arriving in America.
Which, as he said, didn't turn out well for the Native Americans.
Exactly. He thought the risk was far too great.
And finally, his warnings on artificial intelligence. He saw it as possibly the biggest event in our history, but also maybe the last.
And his fear wasn't about AI becoming evil, like in the movies. His fear was about AI becoming competent.
Competent, but with goals that aren't aligned with ours. Precisely. If a superintelligent AI is programmed to, say, maximize paperclip production, it might turn the whole planet into a paperclip factory, not out of malice, but just because that's its goal, and humans would just be in the way.
He also saw the immediate economic threat.
Oh, absolutely.
Yeah.
He argued that if machines are creating all the wealth, that wealth has to be redistributed. Otherwise, you'd have catastrophic inequality that would tear society apart long before the AI took over.
Even in his final days, his mind was still working, still publishing.
It was. His last book, Brief Answers to the Big Questions, came out after his death, summarizing all these final thoughts, and his final research papers were still tackling the biggest mysteries in cosmology.
He died at 76 on March 14th, 2018, and the recognition he received in death was just immense. He was interred in Westminster Abbey.
His ashes were placed right between the graves of Isaac Newton and Charles Darwin. It's a statement. It puts him in that tiny pantheon of figures who fundamentally changed how we see the universe and our place in it.
And his memorial stone has an equation on it. That's his epitaph.
The Bekenstein-Hawking entropy equation. He specifically requested it 15 years before he died.
It looks incredibly complex. Why that one equation? What does it represent?
It represents his entire life's work, his ultimate synthesis. The equation links the entropy or information content of a black hole to the area of its event horizon.
But the key is in the constants, right? The letters in the equation.
The key is in the constants. To make it work, you need the Adler, the gravitational constant from Einstein's general relativity. You need the Pearsall, the speed of light, also from relativity. And you need d Otter Planck's constant, which is the fundamental constant of quantum mechanics.
So it's the one place in the universe where all the great theories have to come together.
It's the one equation that proves that gravity, relativity, and quantum mechanics are all deeply and fundamentally connected. It's the perfect capstone for a man who spent his life trying to build that bridge between the immense cosmic world and the tiny quantum one.
A staggering final statement. So as we wrap up this deep dive, what's the final thought for you, the listener? Hawking's life was this incredible synthesis of the immense and the intimate. He was uniting cosmology and quantum mechanics while his own body was collapsing. So if his Hartle-Hawking state is right, if the universe has no boundary in time, no true beginning, then how should we value this one finite life we've been given? And what grand synthesis should you be striving for in your own deep dives to unite the different parts of your own knowledge and your own life?
A challenge worthy of the man himself. Thank you for joining us for the deep dive.
We'll see you next time.